So, for today, click and close. Get your notes out. It might be worth writing a couple things down. So this is the handout I gave you yesterday. Anybody not get the handout? Yeah.
Redmond, you either. Raise your hand.
Okay, I'll have to print some more.
Summer Redmond.
I have to print some more. Hold on, here's one more.
Summer.
You good? Thank you, everybody. Okay, so I'll print more, but this is, if you go to Moodle, this is the calculus Moodle, and you go up the top, it should say derivatives, standard forms, and it'll put the date as like 12/18 or something, 2019. So that's the updated version. You can just print it out from there. I'll print some more. Remind me before we go today, and I'll print some more out. Okay, so this is, and this one we already know, don't we?
Yes.
Right, so this one we can just sort of omit for now. That one we already know. All this stuff is new though, right?
Yes.
Okay, now where did that stuff come from? Remember the other day?
The unit circuit.
You kind of, right? So where this came from, I think we did arc sine, right? And this is, I want to just remind you how this works because there's a really easy way, and you even did one sort of approaching this on the homework, not quite the same thing. But if we want to find the derivative of arc sine of, let's just take x for a second, then we can always chain rulify it by just putting u's and u primes in there instead, right? By just extending this using the chain rule. But we want to come up with the pattern. So if we want to find the derivative of arc sine x, and the first thing we want to do, if we're trying to develop this derivative formula, well, we don't know it yet, right? So we can't write the answer directly. That's what we're trying to find. But we could rewrite that equation in the form where we're using a sine instead of an arc sine. Never talked about this the other day. So the step then, and this is where you guys seemed like you were a little bit rusty on this, right? So the way you got to think about this is arc sine is the same thing as inverse sine. And how do you undo any inverse function? Well, any function, you take the inverse of that function. That's what we do in math all the time. When you're solving for, like if you were to do shift gears for just a second here, like if you had something like x cubed equals 8, what's the answer? How'd you get 2? Yeah, I mean, it's so, your intuition is strong here. Force is strong in you, I guess, right? There you go. Because you've done this so often, you just know the steps to do, but think why you're doing that. What is the step you go through? You can tell me that the answer is 2, but what is it that you're doing? You're taking a cube root. And why are you taking a cube root? Because the cube root function is the inverse of the cubic function, right? So the missing step that you don't even show there is the step, the cube root of x cubed equals the cube root of 8. And because those are inverse functions, they undo each other and you just get x, right? You get the idea? Okay? So we're doing the same thing up here, right? We're trying to, we want to write this in a way using some function other than arc sine. Well, how do you undo an arc sine function? You take the inverse of that function, which is sine. Remember that it's not a one-way street. We could say that the cube root is the inverse function of the cube function, but it goes the other way too, right? I could do exactly the opposite thing. If I started off with an equation where we had the cube root of x equals 2, and we want to solve that, what would we do? Well, you cube both sides, right? Because you undo the cube root by applying its inverse, which is cubit, right? So they're inverses of each other. Really, it's not like one is the function, the other is defined as the inverse function. They're both functions. They're inverses of each other. Okay? So if we take the inverse of both sides, what's that going to do? We end up with the sine of y equals sine of inverse sine of x, and the sine and the inverse sine undo each other, right? And so what we end up with then is sine y equals x. That's the equivalent way of writing this, with a sine instead of an inverse sine, right? Okay? So now all we have to do is just to find y prime. This is something we can deal with because we know how to differentiate a sine function at this point, right? After we do this process, well, then we can add this to our list, and now we don't have to do it anymore. Now we've got a formula for differentiating an arcsine function. But as of a couple days ago, we didn't have this. We had to come up with this formula, right? So when I do this derivative implicitly, what am I going to get? Well, there's two layers to this one, aren't there? I've got a sine of a y. So what's the derivative of sine hand? Cosine hand times derivative of what's inside, y prime, equals the derivative of x, which is 1. So we end up then with y prime equals 1 over cosine y, which is my answer, but that's a little cryptic. We don't want our answer in terms of y, we want our answer in terms of x. And so to get that answer in terms of x, this is where, remember, if we have that answer, then we just go to a reference triangle that relates all of the trig functions. And where did we start with this one? We started with this one being, wasn't it sine y equals x, right? So if I make a reference triangle that defines that trig function, well, we always feed a trig function an angle, right? That's the input of the trig function has to be an angle. So everybody agrees that y has to be an angle in that right triangle, okay? What's the SOHCAHTOA relationship for sine? Opposite over hypotenuse. So then we know that the ratio of sine y must be the ratio of the length of the opposite side, opposite leg, divided by the hypotenuse, right? So that ratio is x divided by 1. And so now by the Pythagorean theorem, I can find that missing side pretty easily, right? The missing side, I know that x squared plus blank squared equals 1 squared. So this must be the square root of that squared minus that squared, right? Okay. So now what's cosine y? Well, cosine, the SOHCAHTOA relationship there is adjacent over hypotenuse, right? And so we end up with y prime equals 1 over that trig ratio, right? Cosine y equals adjacent square root of 1 minus x squared divided by 1. Well, the 1 doesn't do anything, does it? Right? And so we end up with that result. Okay? We could do that same process for all of the trig functions. It's the same thing. And we just would get these 6 results, right, by using ratios in our reference triangle and derivatives that we know how to take. I'm not going to do that. I mean, you could if you wanted to, but it would just be the same process. But now we've got all these things. Let's practice using them a little bit. Okay? Because like anything else we've done, think about all the derivative standard forms we've added this year. We get a new rule, and then we practice using it, right? So let's practice using these a little bit. And there are some interesting applied problems at the end we'll be able to take a look at. And you kind of get a sense that, okay, this is pretty powerful. There's some stuff we're going to be able to do here now that has some very strong practical applications. Okay, so what about something like this then? Yeah, we're just doing chain rule, aren't we? Right? But we got to remember, so from your sheet, what is our standard form for cosine? So the derivative with respect to x of cosine u equals what? Okay, so u prime over, I mean, I just want to know, just in general, what's our, so it should be on your purple sheet.
For arc cosine? Oh, is that the square root of?
We're just doing ratio.
Oh, sorry, yeah, you're right, what am I doing? We're going to want to have,
We were confused.
yeah, no, you're right, I was confused there, wasn't I? We're going to need it eventually, but we're not going to need it right now, are we? So let's So this is just a regular problem so far, right? We've got a cosine of hand, but inside the hand, we've got an arc sine, right? So at the first level, we don't need anything, do we? First level, when we differentiate, the derivative of cosine hand is,
Negative sine hand.
okay, negative sine hand, and hand is just arc sine of 7w. Okay, so now we peel that away and we look inside. So what's the derivative of hand? Well, the derivative of arc sine of 7w, arc sine of u, right? Arc sine of u is u prime over the square root of 1 minus u squared, 7w squared. And so really, then the third layer is what's the derivative of u? So the u prime that goes on top is what?
7.
There you go, right? So that's our answer. Okay?
And would you need to simplify it from there?
You do. So we want to go further. So what could you do here? Anybody see something that could make this look a lot easier?
Multiplying signs can.
Okay, now we're not
Have a
multiplying,
Distribute.
but so say it differently, Jenny. You're on the right track. But how do you say that? Because that's a common thing, and I want to correct that. We're not multiplying sine by sine here. We're taking a sine of an inverse sine. It's a function of a function, but it's a function of its inverse, right? And so what happens? The sine of inverse sine of you name it is what? You name it, right? It's whatever's in the middle. The sine of the inverse sine of hand is just hand. They cancel each other, right? So we end up with, so we get this negative 7w, right? Times whatever this gives us. So this is going to give us 7 over the square root of 1 minus 49w squared. Right, so our final answer then would just look like negative 49w over the square root of 1 minus 49w squared, right? And then we'll see if that's exactly what we got. Should be, yeah. Okay? Make sense? Okay, so now we got to add, we need another standard form. So let's write this down. We haven't worked with this one on the board yet. So tangent, the derivative with respect to x of arc tangent of u is what? U prime over 1 plus u squared. No square root, right? Okay? So all we have to do is this is pretty easy. We're just going to apply that. U in this case is 9x, right? So y prime just equals, we got the 2 out front, right? 2 times the derivative of arc tangent u is just going to be, we get 1 over 1 plus u squared times u prime, essentially, right? So the u prime will be kind of our last step. So we get 1 plus the quantity 9x squared times the derivative of 9x is 9. So there's my u prime, right? So I just get 18 over 1 plus, 81x squared. Okay? Okay? They didn't even expand out the 9x squared. Okay? All right? Another one. Okay, we gotta do chain rule, right? So you always have to ask yourself, and are you starting to see, I know this stuff looks, at first it just looks overwhelming, there's a lot of rules. But derivatives, just following rules, right? You're just gonna pick the right rule and follow the rules in the order prescribed by the chain rule, right? Just working from the outside in the function, peeling the layers off. So the outer layer is what? Natural log. Okay, so we know natural log, derivative of natural log is what?
Prime over
U prime over u. Okay, so we're going to end up with with a u prime on the top that we haven't got yet, right? We haven't gotten there. Over u, well, u is just arctangent,
Yeah.
right? So on the bottom, u is just what shows up inside the log. So inverse tangent of 8x to the fourth. Okay, now on top we need a u prime. Well, let's just do it this way. Let's just put a 1 on top and multiply by u prime. So we can separate the links here a little bit. Okay, so now the next layer is the derivative of inverse tangent of hand, right? So the derivative of inverse tangent of hand, we just did that rule. It's that one, right?
Yes.
It's 1 over 1 plus u squared times u prime. Okay, so we get 1 over 1 plus u squared, 8x to the fourth quantity squared, times, and we'll just stack this on top. The derivative of 8x to the fourth is what? Okay, and when all the dust settles, then if we write that as one big derivative, what are we going to get here? 32x cubed over, I mean, this, nothing really simplifies too much, does it? I just get inverse tangent of 8x to the fourth times the quantity, 1 plus 64x to the 8th. Okay? Nothing else I can do to that one, right? So you gotta, and I know in a moment of weakness, when your brain is focusing on 14 different things in a problem, there's a tendency sometimes to interpret that as a negative 1 power, right? It's just inevitable that at some point you're gonna lose track and you're gonna do that. So don't though, right? That's why sometimes it's preferable to write it as an ARC, arctangent, instead of a tangent to the -1 notation. They mean the same thing though, right? Okay, and let's just verify we got the same thing, did we? Yeah, good. Okay? Okay? Nice. So now we got a secant, right? Inverse secant. So we gotta look to our purple sheets and we gotta have another standard form. So what's that one?
The absolute value. Square
U squared
minus
1. Okay, good? Okay, so let's apply that. So really, this is just another chain rule instance where we've got inverse secant of hand, okay? So y prime equals that, right? So we'll put the u prime separately. So I get 1 over absolute value of u right? Times square root of u squared minus 1 times u prime. The derivative of 5 times the log of 9x. Okay. Well, first of all, how could I simplify? I mean, we could do this by just u prime over u if we wanted. It's going to be, but if I want to rewrite the log of 9x, what is that? If I use my properties of logs to make this easier.
9 plus
Log 9
plus
plus log x. Okay. That's a little bit helpful. Either way is going to work, though. So then what am I going to get for the derivative of this whole thing? Well, I've got my 5 out front that just stays there, right? The constant is just multiplied by the derivative of the function. So I'm going to get a 5 times the derivative of log 9x. Well, let's differentiate that instead. What's the derivative of log 9? How come?
Because the top.
Okay, true. But we don't even have to, I mean, what is log 9 at? Are there any variables there?
Yeah.
Isn't log 9 just a number?
Yes.
Right, that's a number we would just plug in our calculator again. We don't know what it is, but it's still a constant. So the derivative of a constant is 0, right? The derivative of log x is just 1 over x, okay? So we're going to get 5 times 1 over x is just 5 over x, okay? And there's our answer. Okay, but can we do anything here? Can we do anything at all to simplify this? That's the next issue. So let's take this stuff one at a time. Well, on the top, we've got a 5. What about on the bottom? What about the absolute value bars? Do I need them? I do, don't I? You always have to ask yourself that. Do I need it? Because sometimes you don't. Like, what if inside there we'd had something like an x squared? Would I need the absolute value bars?
No.
I wouldn't, right? Because x squared is always non-negative. So the absolute value never does anything. But it could do something for a log function, couldn't it? Right? There are some, if you think about what a log graph looks like, the parent function for log just does this, doesn't it? Right? So there are some output values that are negative. So we actually do need it for that, okay? We do need it there, so we can't get rid of that. And that's, you're probably wondering, why is it that? But that's something you always want to try to do. Absolute values are, you know, they're just a pain, right? When you're doing math, it complicates things when you have absolute value bars. So whenever you can, you want to always ask yourself, okay, can I get rid of those? Because I don't want them there if I don't need them, right? But we do need them this time. So I think we're pretty much stuck with this, aren't we? All we could do is just expand that out. We wouldn't do it, right? But we could. Just too much writing. Okay, so now we get to an application, right? And this might seem like it's just out of the blue, but this is actually leading us towards our next topic. Is a really cool one. Our next topic is related rates, right? And so when you think about related rates, this is where calculus starts to shine. This is where you start to realize, okay, this is really different than any math I've ever done before, because we're actually able to do something dynamic here, whereas before we wouldn't have been able to. And the example that we'll go back to after break, just to give you some appreciation for where we're going with this kind of stuff, is if you were going to try to describe, I may have already even brought this up, I think I did, I remember talking about this, when we talked about using derivatives as ways of describing rates, right? A derivative is always a rate. Remember the idea that if you're going to blow up a balloon, when you blow up the balloon, like if you're for a kid's birthday party or something, you blow the balloon up, that first puff into the balloon is always really satisfying because the balloon just gets really big really fast, right? But after a while, it gets old, because after a while, when that balloon starts to get bigger and bigger, every time you exhale a breath into the balloon, you hardly even notice any difference, right? Now, why is that? Why is that?
The volume increases faster than certain speeds.
Okay, because you're exhaling a certain fixed volume into the balloon, right?
Uh-huh.
But if you look at the ratio for a balloon, the volume changes at a different rate than the radius of the balloon does, right? In fact, we know what the relationship is: volume equals 4/3 pi r cubed, right? So every time you have to put a lot of volume into a balloon to change the radius a little bit once the volume is pretty big, right? You get the idea?
Yeah.
And so if you wanted to kind of quantify that relationship, which is important, then you'd have to, that's where calculus becomes essential, because the only way to really describe that is to relate those rates of change. We want to be able to relate the change in the volume to the change in the radius of the balloon. And it's not going to be a linear thing. It starts off being, early on, you get a rapid increase in radius for a relatively small change in volume, but when that balloon gets really big, it completely changes, right? And so when we want to be able to use that, quantify that in a way where we can relate those rates and do something with it, the rates are essential, so we need calculus, right? So that's where we're going to go with this, and we'll spend a lot more time talking about it. That was very brief. But this kind of sets us up for that a little bit. So a boat is being towed towards a dock by a cable that's attached to a winch up here, right? And the winch stands 15 feet high above water level. So theta is just going to be defined as the angle of inclination, which is always just going to be the angle between the line and the horizontal in this this case, right? It's always between the horizontal, the angle of inclination. Or the angle of elevation, sometimes it's called too. Angle of elevation of the winch. And let L be the length of the cable as the boat is towed towards the dock. Okay, so ask yourself, what quantities are changing here? Which ones are variables and which ones are constants in this triangle? L is changing, isn't it?
Yeah.
Right? Because as we're pulling in the rope, that distance is decreasing.
And then that means theta.
So theta must be changing too.
Yeah.
Everybody agree? What about the height of the triangle? That's a constant, isn't it? Right? So it's a good habit when you're writing these triangles to relate these quantities. It's a good habit to always write constants as numbers, so you know that they're not changing, right? But anything that's written with a symbol is going to be a variable. Okay, so this triangle, and we really don't need the complicated picture up here. All we really need is just that triangle, right? There's our variable theta, there's our variable L, and that's a 15. Now this quantity down here would be a variable, wouldn't it?
Yeah.
I'm not going to write it though because I don't care about it. I don't write it unless I need it, right? That's not what we're being asked to find. Because if you read the question, if we go a little further with this, it says what's the rate of change of theta with respect to L? Well, the only variables mentioned are theta and L. We don't care about this. We could call it X or something. And maybe in a different question we want to know what that is, but we don't need it in this question, right? So it says, well, what is it first of all? So let's calculate that rate of change. Calculate that rate as a function, and then we can evaluate it for different values of L. Okay? So how are we going to do this? There's a triangle. How are we going to come up with an equation that we can differentiate here, that relates L and theta?
You know that sine theta equals 15 over L.
Okay. So by SOHCAHTOA relationships, we can see in this triangle, theta is the angle. We know sine theta equals opposite over hypotenuse, right? Equals 15 over L. Okay? That's good. Look, we've got an equation there that involves thetas and L's, and now because we have the ability to differentiate implicitly, if I want to get a d theta dl, what am I going to differentiate everything with respect to up here? Right? If I want a d theta dl, we'll call that theta prime, I need to differentiate with respect to L, so when I do the chain rule, I'm going to get a theta prime popping out of that, which is a d theta dl, right? Everybody get that? So we got two options, really. Do we even really need to have the arc sine formula? Not really, because we could just use implicit differentiation here, couldn't we? Right? So let's do this problem two ways. Let's find theta prime, or d theta dl, without using the arc sine derivative formula, and then we'll do it with the arc sine. And you can take your pick. I wouldn't personally. I would just do it without, but either way. So what if I implicitly differentiate with respect to L? What am I going to get on the left side? Derivative of sine hand is cosine hand, right? So the derivative of sine something is cosine something. So I'm going to get cosine theta times the derivative of theta with respect to L is my theta prime that I'm looking for, right? Equals, well, this is just 15 times L to the minus 1, right? So what's the derivative of 15L to the minus 1 with respect to L? Now, these aren't normal variables, but if I'm differentiating a function of L with respect to L, that's normal explicit differentiation, right? Back a month ago or a month and a half ago, we would have done the same thing with X's instead of L's, right? So what do we get? Negative 15 L to the negative 2, right? And by the chain rule, if I went the extra step, I just get dl dl, which is 1. It doesn't do anything, right? So there's our answer with theta prime. If we write that out, we get, I'm going to do this. Let's go. Get right out of room here. Oops. Okay, so if we want to solve for theta prime, I could divide each side by theta, by cosine theta, but that's not really what's being asked, right? We want to be able to plug in values of L. So we want this answer in terms of L. Everybody get that? Okay, we want to be able to plug in L equals 50 and get an answer, 30 and get an answer, 16 and get an answer. So we need theta prime as a function of L. So cosine theta times theta prime equals negative 15 over L squared. How am I going to get rid of that theta there?
Are you gonna take the inverse cosine,
No. I'm not. Because the inverse cosine of all that's going to be a mess. And if I take the inverse cosine of this side, I've got a theta prime inside my inverse cosine. But think about this now. Here's the trick that we've used a couple times. If I want to get rid of a trig function of an angle, go to the reference triangle, right? What is cosine theta in terms of my triangle up here? Okay, cosine of theta is just adjacent over hypotenuse, right? So all we'd have to do is just fill in this missing side up here, and I could write cosine theta as a ratio of sides of my triangle, right? So what is this missing side going to be? Square root of L squared minus 15 squared, right? And so now I could rewrite this whole thing. I could just rewrite that as the ratio of square root of L squared minus 225 over L times theta equals negative 15 over L squared. Theta prime, sorry. Okay? And then all I got to do is divide each side by this, and just multiply by the reciprocal, and I get an answer. Theta prime equals negative 15 over L squared times the reciprocal gives me L over square root of L squared minus 225. I can cancel an L, right? And then I just plug and chug. Just plugging in values, right? I'm just trying to evaluate that derivative, okay? So that's one route. What's the other route we could take? Rather than picking this parent function, what else could we do here? Or I could even start with this one, for example. Like I could start with this parent function. And everybody see what I could do is I could solve for theta there by taking the arc sine of both sides.
Yeah.
Okay? All right, so I would just get theta equals arc sine of 15 over L. And then I could just differentiate directly because I now know the formula for derivative of arc sine. Either way. Okay? All right. Are your brains tingling? Are they hurting a little bit?
Yeah.
Okay, that's good. That's good. No pain, no brain gain.
Hurts.
Questions?
I'm with you. You want